let's get started. So this what we did in the past is this. Last time we were talking about the transfer function GS. So what is the transfer function? S plus 2 over S plus 5, right? Then our input was step function. Step function can be represented by 1 over S, right? Then what is your CS? We know GS is CS over RS, right? So this implies CS equals RS GS, right? So what is your RS? RS is 1 over S. And what is your GS? S plus 2, S plus 5. So we have that. Then if you take the inverse Laplace transform, yeah, if we take the inverse Laplace transform, then what do you get? So this is your GS, right? This is your CS, right? CS equals, take the inverse Laplace transform, what do you get? CT, right? CT equals, what is the thing? What is the, well, we have to do the partial fraction again, right? It's not that easy, okay. We did everything last time. So if we got the, if you do the partial fraction, what you get here is, if you have your lecture note from last week, we got this. Yes, plus 5. That's what we got. So then take the inverse Laplace transform, which is CT equals 2 over 5. Inverse transform of this 1 over S is 1 plus, what is the inverse Laplace transform of this guy? 3 over 5. What is this? E to the negative 5 t, right? Okay, we got up to here last time. So we found this relation last time. Now I'm analyzing this guy here. So this is so I'm analyzing these two guys now. So I don't need this anymore. Okay, so I'm going to analyze these two guys here. So this guy and that guy, right? This is 1. I will call this is 2. I'm comparing 1 and 2. So here, can I write this guy as S minus 0? Right? And how do I write this guy? I can write this guy as S minus 5. Okay. Now the thing is, so this bottom one gives me the pole, right? So bottom one gives me the pole. So here, what is the pole? 0. Here, what is the pole? Negative 5. Okay, so pole is 0, meaning you have the pole here. This is the, I'm talking about, this is input, right? This is the 1 over S is input. Okay, and you have S minus 5, which is output, right? So not output, system, right? Okay, because C, remember CS is S plus 2, S plus 5. We started with this C, right? So this can be written as S minus 0. That's what I did. And this is S plus 5, which is S minus 5. That's what I did. Okay, so you have the pole at 0 and you have the pole at minus 5. So this pole is system pole. This pole is source pole or input pole. I should have said input rather, okay? So input pole 1 over S. That's why pole is at 0. Okay, that's how I indicated 0 here. Then similarly here, the pole is as -5. So system pole, I'm talking about just a pole, okay? Pole and pole. So then you have -5 here. This is -5. Okay. Now similarly, if I talk about the 0, what do I have on the top? I have to do this. So 0 is -2, right? S minus -2. So this is -2. So that's why this is my 0, system 0. Now I'm talking about 3 things together. Input pole, system 0, and system pole. Okay. Now once you see these guys, right? It's 1 and 2. Is 1 and 2, right? 1 and 2. Actually, they are this guy. Okay, this is 1, this is 2. Let me erase this also. It's the same thing. Okay, now what I'm trying to say here is once you know the pole, this is 0. Okay, once you know the pole and the 0 of the system, pole and 0 of the system as well as pole of the input, then you get the output. See, that's what I'm trying to show you. Because, so this is your Laplace transform, right? Look at this. So these 2, remember you had 2 over 5 on the top, right? This 2 is coming from this 0, system 0, which is -2. System 0 is -2, right? That's what this 2 is. This 2 is system 0, this guy. Okay? And this 5 is coming from system pole. See, this is 5. Similarly, so you have 5 and this is 3, right? 5 minus 2. 5 minus 2 is 3. Similarly here, this -0 is coming from here. And this -5, which is coming from here. So you don't have to even do the partial fraction. I mean, it's easy to understand, figure out the output once you know the pole and zeros. That's what I'm trying to say. Okay, they are very related to poles and zeros.
Can you talk about real quick how we got the input pole, the system 0, and the system pole? What was given to us again?
Okay. So we'll go ahead.
So yeah, I was just wondering, making sure that I understood how we got the
yeah, this is given
the fractions and stuff. Okay, gotcha. It's given to us.
This is g equals s plus 2 over s plus 5 is given.
Yeah.
And rs, you have to choose 1. And for the test purpose, we can choose the simplest one, which is 1 over s.
Okay, gotcha.
So then your c will be s plus 2 divided by s plus 5.
Okay. Awesome.
All right. Now I see there are 2 kinds of solution here. One is from the system, input pole, right? This related to system pole, input pole. This is related to input pole. This is related to system pole. So if you take a look at the bottom only, right? So that's let's see the bottom of this. This 0 is coming from, here, which is input pole. And this guy is coming from here, which is this guy, right? Then, so this solution, finally we got the solution, right? See, in the form of t, that's the solution, okay? So when you get the solution, one solution is coming from input pole, that's the one, right? So that solution is called forced response. The thing that you get from the input, because input forced us to get this one. That's the one meaning, okay? This is coming from input. It is the input that forced us to get this guy. That's why we call forced input response, right? Then the other one is for the natural response. Without the input, we got some response. That's the natural response. This is without the input, and due to the input, you have this one. Okay, that's the forced one. So we call forced response and natural response. Okay. All right. So that's what we did. So we already said one is the forced, the other natural. We already did that. So now I want to generalize. So last time we had, so what is the equation we had before? We had CT equals 2 over 5 plus 3 over 5 e to the negative 5t, right? That's what we had in the previous slide. So this is forced, so this is natural. Now, in general, we have here e to the negative 5t, right? In general, you can have e to the negative alpha t. In general, okay. I'm talking about that thing now. Where alpha is the pole location on the real axis. Okay, negative alpha is the pole location on the real axis. Remember, we had negative 5 here, right here. Now we have negative alpha. Okay. And this always generates the solution like this, k times e to the negative alpha t. So only thing is that you have to figure out k, which is constant, right? So if you want to see the nature of solution, you don't have to even, you can even consider k equals 1, right? So it easily gives you the nature of solution. You don't have to solve all those things. Just find the pole and it gives you the nature of the solutions. So how cool is that? Okay. Farther to the left of a pole is on the negative real axis, the faster the exponential transient response will decay to 0. That's what I'm trying to show you here. So if it is negative 5 is here, negative 2 is here, right? This is negative 2, this is negative 5. Farther this is away, it decays fast. Okay, this is a negative. This is the exponential negative 5t. This is the exponential negative 2t. Okay, so farther away meaning it decays faster. This guy is farther away. That's why this decays faster. That's what I'm trying to show you. Now we're excited. Now what we did is, once we know the pole, right? Once we know the pole, we can find the solution. It's very easy, right? Okay, that's what we figured. Now, so I gave you this. Now let's figure out the solution. So what is your CS here? What is your CS? CS will be, because GS equals CS over RS, right? Then what is your CS then? CS equals GS RS. GS is S plus 3 over S plus 2, S plus 4, S plus 5. Then you have RS. RS is 1 over S. So let's put S here instead of at the very bottom, because S is S minus 0, right? So that's why I want to match the order. So S minus 0, S plus 2, S plus 4, S plus 5. Then if you do the partial fraction, what do you get? What you get is, you got some constant on the bottom, sorry, top, then S, right? One for this, the other for this, other for this, other for this. So you have 4 of them, 1, 2, 3, 4. And the constant, I call them K1, K2, K3, K4. Okay. So then definitely this is the forced response, and the other 3 are the natural response. So if you take the inverse Laplace transform, what do you get here? You get C as ECT, and this guy is K1. Then S 1, right? 1 is there. So 1 over S is 1. Then what is the, then K2? What is the inverse Laplace transform of 1 over S plus 2? E to the negative t. Then what is the inverse Laplace transform of 1 over S plus 4? So what is the inverse Laplace transform of this guy? Again this. So then you have K1, K2, K3, K4, K1, K2, K3, K4. Okay. So K's are constant, right? So if you want to know the nature of the solution, you can simply put 1 here, 1, for simplicity, or 2, whatever. Then you can see what is the nature of the solution without doing all those, difficult stuff. The solving differential equation is a lengthy process, right? So once you know this pole thing, right? Pole line zeros, then it's easy to guess the differential equation. So if you have taken a differential equation already, you will appreciate this very much, this method. So Lucas, do you have any comment on this?
Lucas, he went to the restroom.
Oh, okay.
He just sent me a text.
Oh, okay. All right. All right, let's do the first order response. Now we know how the poles and the zeros work, right? So now let's do one by one. Let's do the first order response, then second order response. Okay, first order. So we have done first order, second order already in chapter 2, right? So a lot of thing. So in the second order, we have x dot kind of thing, right? Dot, dot, dot. Then in first order, we have simply dot, right? The highest order is the first, right? And in second order, we have double dot, okay? So let's begin with first order. For the first order system, let's say the system without zero. Let's make our life easy, okay? So a system without zero, meaning, let's say your Z is, you have something on the bottom, right? But on the top, you don't have zero, meaning let's say it's simply A. For simplicity, just choose exactly same A here on the top and here on the bottom, okay? So let's choose a system without zero, meaning there is no zero here. If you have, let's say, S plus B, then your zero will be negative B, right? Your zero will be negative B. But you don't have zero here, so simply A. There is no S component. That's what it means, okay? So now in this case, so what do you do, okay? So how do you utilize those poles? Okay, that's what I'm trying to say. How do you utilize the poles in the case of first order system? Okay, let's say this is your G, and what is your R? Again, let's choose the simplest one, 1 over S, right? That's the simplest one. So if R is 1 over S, then what is your C? C is RSGS, which is A S S plus A. Then if you do the partial fraction, what do you get? Help me here. If you do the partial fraction, so you have 1 for S, the other one for S plus A. So you have S and S plus A. Then on the top, you have B and C. I don't know, these B and C are constant, right? Then you take the LCM here. This guy's LCM, right? Then this guy multiply with this guy, and this guy multiply with this guy. So this B times S plus A, B times S plus A, C times S, okay? So that's what I have here. That's what you do. Then these guys cancel out. These guys cancel each other, right? Then you have A on here on the left, and you have this on the right hand side. Then you have A equals BS plus A plus CS. This is again partial fraction. I didn't have to do it, but I did it. So then how do you get the partial fraction here? If you S equals negative A, what do you get? S equals negative A, then this guy is 0. Then you get A equals C negative A. So what do you get here? C equals negative 1 from here. Okay, then what happens if you put S equals 0? If you put S equals 0, so this guy will be 0, and this is 0. So A equals BA. A equals BA. Then what is your A? Sorry, what is your B? B is 1. So B is 1, C is negative 1. We got that. Then you have to put in here B is 1, C is negative 1. Okay. So if you do that, you got this one here. Makes sense? Now, so remember in the first order, we just have S plus A, okay? So if you have second order, you'll have S plus A, S plus B, okay? That's the second order. You have a squared term here, okay? So in this case, you don't have that, so that's why this is first order. We started with the first order. Then what is the Laplace transform, inverse Laplace transform of this guy? This is equal to C, right? This is equal to CS. CS equals to 1 over S minus this guy, right? That's your CS. So what is the Laplace transform, inverse Laplace transform? CS is CT. Then what is this guy? Simply 1, right? Then what is Laplace transform, inverse Laplace transform? This guy. You have this, right? Makes sense so far? Then you can call this guy is this guy, and this guy is this guy. Forced and natural, right? F means forced, N means natural. Okay? So your forced response is 1, and the natural response is this. So far, so good. Okay?
I have a quick question.
Please.
So when we talk about a forced response versus a natural response, and look at that in terms of a real life system, are we saying that the forced response is the input, is the response that we're causing, and then the natural response is just the response of the system?
Natural without the input.
Gotcha. Okay.
Makes sense?
Yeah.
Okay, good. Now, once we have this relation here, I will use this relation and define some quantities here, okay? What I'll define here is, so I'll take this guy here. First of all, I'll take this. Okay, then I'll take, okay, so I'll take CT. I'll take CT also. CT is 1 minus e to the minus AT, right? So I'll take both of them one by one. I'll take this guy, which is a natural response, and I take the total response and define a quantity called time constant. Okay, let's define time constant from here. So if you have t equals, let's choose t equals 1 over a. Then what do you get here? If you have t equals 1 over a, what is your C and t? Guys, help me here. E to the, this a and this a cancel out, then you are left with e to the negative 1, which is negative 1 over e. Oh, you know what? I don't want to take this negative sign into account. Just let's say this guy, okay? This guy and this guy. And they are separated by negative sign, okay? You can take it too, but it's negative means it's going down, right? That's the meaning. It's what did I say? Yeah, negative is this sign is negative, right? This guy, sometimes it is negative is coming from here, right? Where? Here. Okay, just this negative is part of the constant, okay? That's what I meant. This negative is part of the constant. So I just take this term only. So if you do that, then your C and T is 1 over E. Then what is the time constant? So when T equals 1 over A, your C and T is 1 over E. This guy is called time constant. Exactly the same way we did in the case of capacitor, right? Remember in capacitor we did the time constant? This is exactly the same way. Okay, So time constant, at time constant, the natural response decays to, if you do that, this is 37%, by the way, okay? So E, if you do 1 over E, you get 0.37 in your calculator, okay? So this is, so the time constant is the time for C and T, right? Time for C and T to decay to 37%. Or at the same time, how do you define the, if you use same thing here, then what do you get here? 1 minus, if T equals 1 over A, what do you get? 1 minus 1 over E. So what do you think it will get? You will get here. You got 37. So 1 minus 37, which is 63. 100 minus, because we had percentage mean 100, right? So the time constant can be defined in 2 ways in that case. So time constant can be defined as 2 ways. So time for this guy to decay to 37%, or time for this guy, 1 minus this guy, I would say rather, this guy. So time for this guy to rise up to 63%. So right here. So this is this guy. E, oops. This guy is 1 minus E to the minus AT, the green. And this guy is, help me, E to the LAT. That's the thing. So what is the time to decay 37%? That's the 37%. See, this guy is 37%. For the red one. Red one decays, right? So what is the time it takes to decay to 37%? Or the time it takes for this green one, which is the total response, to rise to 63%. See, this guy is 63. This is 0.63. So they're exactly the same time. Okay, and that time, this guy here, right here, this time is called time constant. We call it tau. Okay, since my function is what? My function is, my alpha is negative 5t in this case, right? I took alpha equals 5, right? See? So what is your t then? If alpha is t, then t equals 1 over 5. What is 1 over 5? 0.2. See, I got time exactly 0.2. See that? This graph also verifies that my time constant is 0.2. Question here? So since we did the time constant, now let's do the, what is the significance of this time constant, okay? So reciprocal of time constant has the unit of 1 over second, obviously, or we can say frequency also. That's why this A, remember you have e to the minus AT, that A, this is also called exponential frequency. And also, if you take the derivative of this guy, if you take the derivative of e to the minus AT, what do you get? E to the negative AT times negative A, right? See that? So at time t equals 0, what do you get? At time t equals 0, what is this derivative? So this guy is 0, so e to the 0 is 1, simply negative A. See that? So negative meaning the slope is this way, not this way, right? This is the negative, that's the meaning of negative and positive. This is negative slope, this is the positive slope. So let's not worry about negative, because this is negative is meaning this way. So the time constant gives you the rate of change. Derivative is what? Derivative is rate of change, right? So time constant is the rate of change of this function. The time constant gives you rate of change of this function at t equals 0. Or you can say initial rate of change of this guy at t equals 0 is A. or negative A. Negative A means this is like this, okay? This is positive A, because this doesn't happen, this will happen. So it means, what do you conclude from here? What is the significance of time constant then? Time constant somehow gives you the rate, right? So it gives you the rate. So time constant is the measure of system's response. That is how fast it changes. Hence, it is a transient response specification for a first order system. Remember we talked about transient response in chapter 1? Okay, so it's related to time dependent, right? Time depends on, it's a vary with time, right? That's the transient response. So in the beginning, the system has the rate of change equal to negative A. Okay, it means it tells you how fast the system changes. Okay, so it means time constant gives you, specify the transient response. How fast, how slow, that kind of thing. And also, time constant can also be evaluated from the pole plot. Remember this A thing is somewhere here, right? Negative A. Okay, so this A, take the inverse of A, that's the time constant. So you don't have to even do all those calculations. Just from the pole plot, you see the A, and time constant is 1 over A. Okay, that's how you figure out time constant from pole itself. Now next thing is, first thing we discuss is time constant, right? We already did that. Time constant is done. Now next thing I'm going to discuss is rise time, which is called TR. Rise time is defined as, this is just the definition, the time for the waveform to go from 0.1 to 0.9 of its initial value. What is my waveform? My waveform is this, right? E to the, remember my A is 5 in this case, alpha or A, I think we call it A, right? So my A is 5. So if I plot this, what is the time it takes to go from 0.1? What is my 0.1? Right here. This is my 0.1. What is my 0.9? 0.9 is here. What is the time it takes to go from here to here? Because this guy is this guy, and this guy is this guy, right? So what is the time it takes to go from 0.1 to 0.9? This is the time, right? This time is called TR, rise time. Okay, and that rise time can be found to be 1 over A ln n, ln 9, okay? So you can do C equals this, so e to the AT equals what? 1 minus C, then ln ET, take the log on both sides, then T equals this, T equals this, you know that, right? So I don't have to spend too much time on this. So then find the difference between 0.9 and 0.1, then eventually you get this. So if you do that, this ln n is 2.2. If you do the calculator, you happen to find this ln 9 is 2.2. So it means your TR is 2.2 over A. So 1 over A is tau, right? So 2.2 tau. That's your TR. There. Similarly, next thing we'll talk about is the settling time, okay? So TS. So we got tau, we got TR, now TS. What is the rise time? This is the rise time, this is time constant, this is settling time. Let's do the settling time now. Settling time is defined as the time for the response to reach and stay within certain percentage of the final value. Reach and stay. So let's say I want to define the settling time for 2%, meaning my final value remains within 2%. So this certain becomes 2 now. So settling time is defined as the time for the response to reach and stay within 2% of the final value. What is the 2% of the final value? Final value is 1, right? See, this is 1. So what is 2%? Meaning 98. Okay, when it is 98 here, right here. See, right here it is a 98. after it reaches 98, it stays inside 98 because it's going up and up here, right? It never comes down again. So that's why it reaches 98 here and it stays within 98. Okay, so that time is called settling time. Okay, remember my time constant was 0.2. Now in this case, my settling time is now 0.8. So it is almost like four times time constant. Okay, for 2% settling, my thing is almost 4 times time constant. But as a rule, in general, as a rule of thumb, this TS is always less than equal to 5t. In this case, 4t, because my function is this. But in general, it stays less than 5t. Question here? Yeah, this is just, I'm trying to show you the initial slope, which is time constant, right? So this here, right here, I draw the tangent. This is my tangent, right? So that tangent gives me the initial slope, that's all. Okay. Okay, so far so good. Any questions before I go to the second order system? Comment? Question? Yes, no, maybe?
I don't think so.
It's interesting. It's interesting stuff. Seeing all the stuff we can do with just a with that value A. It's
Yeah,
cool to
I
pull
know.
all that information.
Yeah, a lot of information, right?
Yep.
So. Okay, let's talk about the second order system now. So we talked about A over S plus A. That's the first order system. Now I want to talk second order system. I'll consider this is as my second order system. Let's say alpha 1, alpha 2 on the top, again without 0, right? So for simplicity, let's not consider 0. So this is constant, alpha 1 constant, alpha 2 constant. Then yeah, on the bottom is second order, right? So you have to have S squared thing. So this S and this multiply gives you S squared. So you have two terms here, which is second order. So you have S plus alpha, the same alpha, and S plus alpha 2, this is same alpha 2, okay? For simplicity, I chose this, okay? But I can generalize this later on. For now, let's consider this. Let's start with the simplest one. So again, your RS is 1 over S. So you by the help of this system function, right? GS. Oh, I should have said GS here. Sorry. So I can define the 4 different possible response by using this transfer function. So okay, I can show all, mean there are 4 in total possible second order transient response. So who has taken the DFQ already? Lucas and who else? I forgot. We talked about it last time, I think. So Lucas.
What's up?
So you have taken differential because who else have taken it? Anything else? Anybody else?
I think Jane said she had, but it was like a long time ago.
Yeah, that's correct.
Oh, okay. So you two guys might appreciate it too much. Okay, so once I go through this, you guys will appreciate too much. I'm sure of it. So let's see. So you might have remember this kind of differential equation solution in the DFQ. So if you have this kind of solution, right, then that response is called overdamped, okay? Overdamped response. So what happens is how many? Okay, let's not go that far. So how about here? What are the poles here? Alpha 1, negative alpha 1, right, and negative alpha 2. Okay. So are they real or imaginary? So for now, let's consider that real. Let's consider them to be real. Okay. You got 2 poles. Let's consider them to be real poles. Remember Jane and Julkes used to say real root in DFQ.
Yep.
If you have, huh?
I said, yeah.
Yeah, so you need to say real root, right? If you have two roots, real roots, then what is the solution of the differential equation? You can go back to your note, differential equation note, and you'll see that this will be your differential equation, sorry, solution. So here is, we say real poles. So alpha 1 and alpha 2, I would say negative alpha 1 rather, and negative alpha 2, so that they are not equal. If they are equal, there is different story, right? So those who have taken DFQ, if they are equal, we have different story. We will do that too. For now, alpha 1 and alpha 2, they are not equal, and both of them are real. So two conditions, both of them are real, they are not equal. In that case, your differential equation is very easy to figure out, which is K1 times e to the, see, negative alpha 1, this guy, and negative alpha 2, this guy. Make sure they are not equal, right? If they are equal, then you cannot do this. Okay? So that's how you figure out. From the pole itself, you can find the differential equation solution. How cool is that? You just have the equation here, the transfer function. From the transfer function, you can predict the solution to the differential equation. Wow. This is wow to me. Okay, so in this case, this is my alpha 1, this is my alpha 2, right? And this is S-plane, meaning sigma and j omega is there. So when you have two real poles, unequal, right? Unequal real poles, you can view the system as two cascaded first order system with time constant of this and that. This is what I meant. This is what I meant. You can see this is one first order system. This is the next first order system. You can cascade them like this. It behaves that way. Okay, that's what I meant. Now, let's talk about the different kinds of poles now. If the poles are real, not only real, but alpha 1 and alpha 2, they are equal also. Suppose they are equal to alpha. Both of them are alpha. Alpha 1 is alpha, alpha 2 is alpha. That's why your roots are negative alpha, negative alpha. You have two roots, but they are same. If you have this kind of situation, then what is your CT? What is the difference between previous solution and this solution? In the previous solution, you didn't have this T there. See this T? You didn't have it there. But if you have same real pole, right? Then you will have this T there. Okay? T also there. This kind of system is physically, this kind of solution is physically the critically damped response. What is the previous one? Previous one is over damped. Okay? This one is critically damped. So I'll talk about what those systems look like, okay, in a couple of slides. For now, just try to understand what it means, what it is. Then in next slides or so, I will have the exact example of what this critical damping and those stuff. Then let's talk about under-damped system. So under-damped meaning you have the poles which are complex. So remember we have real poles here. Now these poles are no longer real here. We have complex now. When you have complex poles, meaning your poles is alpha, negative alpha plus minus omega d. And J is there because this is complex, right? Then how do you represent this guy here? You represent this guy in the S plane like this. Your J omega d, this is omega d because omega d is plus and minus. That's why one is plus, the other is minus. Okay, and alpha, negative alpha. So this is negative alpha. So what are the poles then? Negative alpha plus omega d here, negative alpha, negative, minus omega d is here. So you have two poles here, this pole and this pole. This is what happens. Okay. Then what is your solution? See, remember this solution. How does it change in this case? In this case, your solution will be A. You could simply say K also. Okay, this is constant anyway. So A times e to the negative alpha t, this alpha, and cosine omega d times t, then phi. You have the new parameter here, right? Phi. What is phi? Phi is something that is defined by this formula, but this formula has xi. Is it? What is this called? Xi? I forgot. I don't know. Why did I forget? It has some name. I think it's okay, but this quantity will be defined later also. Okay, so don't worry about it. So we'll define it later. Now next thing is two imaginary poles. So which is the undamped response. Okay, if you have two imaginary poles, which is real part is 0, right? Imaginary means your real part is 0. So then you have plus and minus omega n. So omega n is here. This is plus omega n. This is minus omega n. So your poles are right there. Two poles. And in this case, your differential, the solution will be like this. Now you might have remembered, at least Jane and Lucas, you might have remembered all those 4 different kind of differential solution. Guys, any comment here?
I do have one question, GV.
Yes, sure.
Mainly just because this part more is like more heavily differential equations than other parts. What's like the main difference when it's like strictly like differential equations from like the class and like mainly just math versus like differential equations in terms of like what we're doing here?
Oh, this is, yeah, we are doing this in the S space, right?
Yes.
Yeah, that's the only difference.
Okay. So everything else is like still the same. It's just like
Yeah, so you
you're
get the same
doing
answer. You get the same answer, but we are this our treatment. Your methodology is different.
Okay, that answers my question pretty much.
Okay, all right.
Thank you.
All right, so now we talked about damped, underdamped, critically damped, and overdamped. So this is what it means. So undamped means, see, they have the same peak here. See, different. Suppose you started with this, right? You started with this. Next peak also exactly the same. This means undamped, right? There is no damping. The underdamped means, see the peak here. This is underdamped here. This guy is underdamped, and this is critically damped, and this is overdamped. Okay, this is the difference. Now, in the previous case, we started with just simple thing, right? Simple alpha 1. What is that? Alpha 1, alpha 2. S plus alpha 1. S plus alpha 2, right? That's what we did in the previous. Now I'm going to do the second order again by considering slightly different transfer function. Okay. So now my transfer function is this. So all of these are this. See, you have S squared here, S here, right? Everything else is constant. Everything else is constant here. Guys, so far so good. Now this guy has pole. This guy has pole. What is the pole for this guy? How do you find the pole? So set it to 0, right? S squared. That's how you find the pole. So how do you solve this equation? ax square plus bx plus c equals 0. What is the solution? X equals minus b plus minus b square minus 4ac divided by 2a. Use the same thing again, okay? If you do that, you will get s equals this here. Okay? Then I can call this guy the alpha. This entire thing is alpha. This is alpha. And this entire thing is, omega d. This is my omega d, right? That's what I say. Now, so this omega, so in the omega, see in the alpha, you have these two quantities multiplied together. So this omega n, by the way, is called natural frequency. And this guy is called damping ratio. Okay, this is called damping ratio. And what is the omega d in the omega t? Omega d is this guy, right? This guy. This is omega d. So omega d is this, and this is called damped frequency. Omega d, damped frequency, omega n, natural frequency, and this is damping ratio. And alpha is 1 over t, right? That's what you know. Okay. So remember we defined theta in the previous, I told you, right? Phi, remember we defined phi equals inverse tangent, right? This quantity here. So this is cosine theta, okay? This guy is cosine theta. Instead of writing this, you could write this. Inverse tangent cosine theta divided by 1 minus cosine theta square. Cosine square theta. Remember we did this before? Let me show you. Let me go back here. Where is it? Yeah, here. Remember? In this slide. So this guy is cosine theta, okay? Cosine theta. So theta, what is theta then? Your theta is this angle here. See? This angle is called theta. Right? Now we can use the damping ratio. Remember, we can use the damping ratio to characterize all those 4 kind of responses, okay? So what are the 4 kind of responses? You have underdamped, undamped, critically damped, and overdamped, right? So they can be defined by J or damping ratio. Is it the correct name to this guy? I'll figure it out, okay? So do you remember this guy? What is the name of this guy? I forgot. So depending on your value of this quantity, you have, if it is 0, then it is undamped. See, is that easy? If this guy is 0, it's undamped. If this guy is between 0 and 1, this is underdamped. If this guy is exactly equal to 1, this is critically damped. If it is greater than 1, then it is overdamped. So that's the significance of this quantity. Okay, so you can define all those 4 responses by using single parameter, which is damping ratio. Any questions so far? So far, so good.
Will that oh, sorry. Oh, will that 0 to 1, that'll always be the case?
If it is between 0 and 1, this is underdamped. Just close your eyes and you can say, okay, this is underdamped case. My system is underdamped.
Okay, cool.
Okay, so if it is 0, so this is damping. Underdamping means, you see the first peak, but then after it will start decaying quickly. Then this is critically damped, and this is even more than that. Okay, that's the cool thing about this parameter. Now let's talk about the Laplace transform solution of the state equation. Now I'll take you back to chapter 3 again. Remember we did this kind of stuff. You must have remembered this thing. This remember we derived this guy as I minus A inverse. We found the inverse, right? Remember the other day? Okay. So I'm taking you guys back to the same problem again, okay? Or similar problem, I would say. All right, so I have state equation. So what are the state equation? We have x dot equals ax plus bu. What is your output equation? This is my output equation. Now let's take the Laplace transform of both of these guys. So what is Laplace transform of this guy? So what is on the right hand side? Let's do the right hand side first. So A capital X, then B capital U. That's your right hand side. How about left hand side? Left hand side you have x dot. What is the Laplace transform of x dot? Sx minus x0. Remember, until now we consider this to be 0, right? Because we're talking about transfer function. For the transfer function, it always 0. But now we are not talking about transfer function anymore. We are talking about state equation and output equation, which is chapter 3, not chapter 2. Chapter 2 is transfer, where we consider this guy to be 0 all the time. But now we don't ignore that anymore. So this is the actual formula for the x dot. Sx minus x0. Okay? So that's what I have here. Sx minus x0 on the left, then ax plus bu on the right. Okay, I'm just transforming this guy, the first one. I transform this guy. Then you can rearrange this guy. So Sx is here, then Ax is here. You can pull this on the left. Then you get Si minus A, the way we did before. Then I want to push this guy to the right. To the right, then you get this guy plus Bu, right? See, you have this guy here. Then from here, if you take factor out Xs, and then you have, okay, so if you divide both sides by S minus, divide means, in matrix divide means take the inverse, right? So then this is what we get. Okay, this guy cancel, then you get this. Okay. So now I did that. Now let's do the inverse transform of output equation. So this is what I get. So y becomes ys. This becomes c times big X and du. Then what is your x? Remember we have x here. This x is this x. Plug this in here. If you plug this in, then this x becomes this guy here. This is exactly this guy. Just pull this down here. Then you have d and u here. Make sense? Then what do you get here? We have, so C. So what I did is I wanna group this together. Okay. So du is du. See, u is there, right? So that's why u is factored out. So then d is here. Then what is this guy here? B is here. Besides B, what do you have? Remember, you have this also there, right? Besides B, that's why you have B and these two guys. These two exactly same. Okay. Then what is the first one? The first one with the x0, right? So this guy with the x0, that's what I have. So that's what I got. Now this is how you find the output equation. Okay, we found the state equation in chapter 2. So chapter 3, we found this. Now we are going to find the solution out from there. Okay, this is how you find the solution. This gives you x, this gives you y. That's how you find the solution. Again, I'm going to introduce some new concept here, which is called eigenvalues of the matrix. So you'll understand what is the significance of eigenvalue in a couple of slides, okay? Eigenvalue of matrix A, this matrix, see this guy is a matrix. So we'll define the eigenvalues of this matrix. How do you define the eigenvalue? If you set this guy equal to 0, remember this guy here, if you set this guy equal to 0, which is this guy, the determinant one, take the determinant of this guy, take the determinant of this guy, and set it to 0. That's what I did here. Take the determinant and set it to 0. After you do that, what are the values of S you get? What are the values of S you get? You get the values of X from here, right? Those values of X are called eigenvalues of matrix A. In a couple of slides, you'll get to know what is the significance of those eigenvalues. Okay? So by the way, if you have this x0 equals 0, what do you get? If x0 is 0, this guy is 0, right? Then you are left with ys equals this. It means, what is your ys over u? Ys over u is this guy, right? This guy only. So ys over u is, by the way, this is transfer function. So you get transfer function, which is exactly this guy. Again, we came back to chapter 2. Let's do one more problem about this, then I'll okay. So let's find that Laplace transform solution, eigenvalues and poles. So the problem is this. Problem is x dot. If you have book, I'm doing this from the book. Okay. Problem is 0, 0, negative 24, 1, 0, negative 26, 0, 1, negative 9, x plus 0, 0, 1, u is e to the negative t, that's your u. Then y is also given there, y is 1, 1, 0, x. Then your x0 is also given. This is the first time you are given x0, remember? 1, 0, 2. Then your goal is to solve the state equation. Solve state equation. The goal is solve state equation. Solve state equation and output, and find the output of the system. And B, part B is find the eigenvalue and the poles, system poles. Eigenvalues and system poles. Let's figure out these two things. Okay. So what is the formula we had? We had the formula. How do you find x? You have to find x and y, right? State equation. So you have to find x and y. So what is the thing we did just before? Your x is, what is your x from the previous slide? X equals si minus a inverse x0 plus bu, right? That's what we did, right? Okay, let's figure out this guy first. Let me change the color. So what is your s minus, so how do you do that? What is your si first? Guys, do you think you can do it? Because we did the similar problem before. if you can do it, that will be great. So let me quickly write what it means. Okay, so Si minus A. Let me write Si minus A. Then you can do inverse, right? That's my hope. Si minus A is, what is my Si? Si is, A is 3 by 3 matrix. That's why Si will be this. S0 0 0 S 0 0 0 S. This is my Si. Then minus A is there. This guy. This guy is A. Okay, if you do that, what do you get? Let me simply write A here. Then I'll give you the final answer. Si minus A equals, then what is the thing? S minus 0 is S. The next thing, 0 minus 1 is minus 1. 0 minus 0 is 0. Then 0 minus 0 is 0. S minus 0 is S. Then 0 minus 1 is minus 1. Then 0 minus 24 is 24. 0 minus negative 26 is 26. Then S minus 9, right? S minus 9, which is S plus 9. Okay. Now what is your S minus Si minus A inverse? Remember we did the adjoint over determinant thing last time. Adjoint over determinant. Si minus A, determinant of Si minus A. So if you do that, I'll just give you the answer. Okay, I'm not going to do it because I did it once last time. So I'll just give you the answer here. So answer will be this. S squared plus 9S plus 26 minus 24 minus 24S, S plus 9, S squared plus 9S minus 26 S plus 24. Then third column is 1 S squared. That's my adjoint, right? This, I got the adjoint, the top one. I got this guy. I got this guy. And what is the determinant? Determinant is divide by, determinant is S cubed. This is what you get. 9S squared plus 26S plus 24. Okay. So now you have this guy, right? Then plug this in here. Plug this in here. But before that, you have to find x0 and bu. What is your x0 plus bu? Find it out. What is your x0? X0 plus bu. So what is your x0? Help me here. 1 0. See? 102, right? 102 is your x0. What is your b? Help me here. What is your b? B is this guy is B, right? This guy is B. 0 0 1 is B. What is your U? This is your little u, right? What is the transform of this guy? Give me the big U. What is the inverse Laplace transform of this guy? Say Laplace transform of this guy. Guys, help me. That's your U.
1 over s minus 2.
S plus 1, right? Because you have just 1 here.
Oh, 1. Sorry.
S
Yes.
plus, yeah, thank you. So 1 over S plus 1. That's your U. So we got this U, we got B. Oh, sorry, yeah, this is what it is. Now what do you get here? So what do you get here? So help me here, guys, I'm lost. 1 plus 0 times this. 1 plus 0 is 1. 0 plus 0 times this. You got 0. 2 plus 1 times this. 2 plus 1 over S plus 1. That's your this guy. So you have to multiply. So this guy is what? This guy is, let me change the color. This guy here is, this guy here is this guy. So you have to multiply that with this, right? This is this. So this guy is right here. This is my this guy here. Then multiply this guy by this guy. What is that one? That one is this guy here. Let's multiply that, okay? Let's do that here. So let's multiply by this guy here. 1, 0, 2 plus 1 over S plus 1. There. Let me erase it. Okay. Now what do you get? If you, okay, now the thing is, so what is your x1? Let's find the x1. What is your x1? X1 is this guy multiplied with this guy. Gives you x1, okay? So can you help me here? Guys, I need your help, okay, please. X1 equals S squared plus 9S plus 26. This guy multiply with 1, right? Then this guy multiply with 0, which is 0. I don't have to write it. So this guy multiply with this guy. What do you have here? Plus 2 plus 1 over S plus 1 divided by this thing here. S cubed plus 9S squared plus 26S plus 24. Okay, so far so good.
Yeah.
Okay, now let's take the thing, the LCM of this guy. What is the LCM of this guy? S squared, S plus 1, plus 9S, S plus 1. So I can add this together, 28. 28, S plus 1, plus 1, divided by S plus 1, then this whole thing here. S cubed plus 9S squared plus 26S plus 24. Let's simplify this guy. Let's simplify this guy. So what do you have here? S cubed plus S plus 9S squared plus 9S plus 28S plus 28 plus 1, right? S cubed S, 9S squared, 9S, 28S, 28 plus 1. Then what is on the bottom? Remember, I want to factor this guy also. So S plus 1 is one of the factors. How do you find the factor of this guy? Let me do this factor and I'll close the shop for today, okay? So what is the factor of this guy? So if you just keep trying from 1, plug in the value of s equals 1, then -1, then 2, then -2. But since I don't have more time, I start with -2, okay? But when you have time, you just start with everything and do whatever I'm going to do now. So s cubed, -2 cubed, plus 9, -2 squared, plus 26, -2, plus 24. So what do you get here? This is -8 plus 36 minus 52 plus 24. See, this is 0. When you put -2 and this entire thing is 0, that means one of your factor will be s plus 2. See, -2 gives you plus 2. That's the thing. So did you guys do this in high school or in linear algebra or wherever? I don't know, how do you factorize this guy? So your goal is to get s plus 2 from here. So how do you get s plus 2? S cubed, then you have to get 2, right? 2s squared. This gives me s plus 2. Then you have 2s squared, but you have to have 9s squared. So you have to add 7 here, 7s squared. Then you have to have 2, right? Again, 14s. This gives me s plus 2, but you have 26 here. Then how much is left? 12. 12s is left. Then you have 24. Okay, so what do you get from here? You get s squared, s plus 2, plus 7s, s plus 2, plus 12, s plus 2. So what is the factor here? S plus 2, then you have factor out, right? You can factor out s plus 2, then what are you left with? S squared plus 7s plus 12. Now if you factor this out, you get 2, you get still 2 factor here. This factor will be s plus 3 and s plus 4. You can do it at home because, you know, similarly you try s minus s equals -3 and this becomes 0, meaning one of the factors is s plus 3, okay? Similarly, that's why my bottom is s plus 2, s plus 3, s plus 4. How much time do we have? Oh, we ran out of time. So do you guys have any question so far? If not, I found x1, then I will find x2 from here. This guy and this guy x2, and this guy and this guy x3. I'll do it tomorrow or next time. Yes.
One quick question. What was the point of grabbing 2? Or what were you?
Okay. So we are factorizing. Our goal is to factorize